There's some pens going around. Make use of name tags. There's an attendance poll, poll 4422 on Piazza. Please sign up. And for those of you who are not aware of this, my classes are always dumb classrooms. Your laptops and phones must all be shut. And the only time I'm going to allow you to open your laptops or phones is when you are responding to polls on Piazza. Some of you like to take notes on your laptop. I would like to permit it, but then I have no idea of whether you're actually taking notes or poking around on Facebook. And trust me, this happens a whole lot. And each time one of you decides that you really, really want to be laughing at the latest post that someone made on Facebook, everybody around you is disturbed. So no laptops, no phones, except for the Piazza posts. Piazza polls. Yes. Attendance poll, Vedant, 422, can you just release it? It should be there. Maybe you haven't released it yet. We typically release it a couple of minutes before class because otherwise you could just respond to it before the class begins and never turn up. It's live, 422. Ah, great, thanks. It's good to see you, Mike. Okay, so the attendance poll is going to be live in a minute. And here, make use of name tags, guys. Yeah. Okay, all of you. Once you're done with your attendance poll, please shut your laptops. All of you. May I have your laptop shut, please? You're not seeing the 422 on Piazza? Michael, is the 422 live? It should be live.
Add 422 in the little search box. Yeah.
It is live. Wait a minute. This is probably the longest class you're going to have. We have 280 slides. So every second that I wait, there's going to be a second that you're going to miss from the end of the class, or a little bit faster that I will speak, which means that you are going to have to struggle to keep up with me. So let's be prompt. Okay, let me begin. You guys, if you're done with your polls, please shut your laptops, right? You at the back. If you're done with your polls, please shut your laptops. Okay, I will give you another minute to respond to the attendance poll. And if your laptop is still open at the end of that, I will wait for you to shut it, all right? Okay. You done? Please shut your laptops. Okay, shut your laptop. You mind? Yeah. Okay, that's fine. All right. Okay, guys, let's begin. So the story so far, we have seen that Multi-layer perceptrons are universal function approximators. They can model Boolean functions. They can be classifiers. They can be regressors. They can be trained through variants of gradient descent. But then, and all the models that we've seen are of this kind, where you have one layer of neurons feeding to the next layer of neurons, and that feeds to the next layer of neurons. Here's a new problem. I give you a speech recording. It's always a half-second long. Now, or maybe a second long. So you know the exact length every single time. And now I'm asking you if this signal contains the word welcome. Now, the obvious thing for you to do is to just convert it to a spectrographic representation like you did for homework 1, and then just stick a multi-layer perceptron on it. It can read all of it, and it should be able to tell you whether the word welcome is present in it or not, right? But then, suppose I have 2 recordings. The first one is 1 second, both of them are 1 second long, but in the first recording, the word welcome occurs in the early portion of the recording, and in the second one, the same word occurs in the latter portion of the recording. Will the same network fire for both inputs? Yes or no? Why not? It's entirely different, right? So to simplify the problem, that entire input can be thought of as a vector. And in the first case, it's like having a bunch of ones over here, or some numbers over here, and zeros out here. In the other case, it's like having a bunch of ones out here and zeros out here. These two are entirely different vectors. They live in different subspaces. The network that fires in the first case will not fire in the second case. And so what we want is a simple network that will fire regardless of the location of the word welcome. And if the word is not present, it must not fire. Now, same problem, with images. We can build an image detector to detect flowers. But then, if I have, let's say, an MLP that can detect, that has been trained to detect flowers in pictures, then an MLP that detects the flowers when they're in the top left corner is not necessarily going to detect the same flower when it occurs in the bottom right, because these 2 data points are in completely different subspaces. And we need a network that will fire regardless of the precise location of the target object. So in many problems here, the location of the pattern is not important. Only the presence of the pattern is important. And conventional MLPs are sensitive to the location of the pattern. So, if I just move the entire pattern by just one position, it means I live in a different subspace. It's not going to fire. We want a network that will be shift invariant. Now, if I asked you to this problem, the answer to this problem, what would be the simplest solution you could think of? Hey. So how do you know where it is, right? You don't. So yeah?
You can run the same network through frames.
You can scan, right? The trivial solution is to say I'm going to throw it all into the training data. So I can have pictures with flowers in the top left corner, shifted by a pixel, shifted by a second pixel, every single possible variant of a position of the flower, and then I can throw it into my training data. But what would the problem with that solution be? It's very simple. It should work. What would the problem with that be? The amount of data is going to increase tremendously, and the complexity of the network that can learn all of this is going to be immense. You would need a very large network. So the alternate solution, as who was it, Rishabh, who mentioned, would be to scan. So I can build a network that looks for something about the size of the word welcome, and then run it at the initial location, and then just scan. And at each position, it's going to look for the word welcome. Now, what will this network do? It's going to output a value which tells you whether it has seen the word welcome at any one of these locations. What I want is to know if the entire recording has the word welcome in it or not. So how can I combine these to determine if the recording has the word welcome in it? Anyone? Yes? What kind of layer would that be?
Another multi-layer perceptron.
A multi-layer perceptron? What? Anybody else?
Meta layer.
A
meta layer.
What is a meta layer?
We combine.
You guys are thinking too hard. What's a simple solution? Well, who was it who said? It's just an OR, right? I can use a max. A max is an OR. If it has found a flower or the word welcome at any one location, then at least one of those must give you a large output. So the max is going to be a large value. Otherwise, it's going to be a small value. And so that's it. Or I can replace the max with a softmax if I'm allowing for some wiggle, right? Or indeed, I can replace it with a multi-layer perceptron. But the basic idea remains. What we are really doing is scanning the input. That clear to everybody? Right. Okay. So what would the pseudocode for this look like? It's simple enough. How does this work? Thank you. So, I'm scanning from left to right. At each position, I'm pulling out a segment of the input that's roughly the width of the word welcome, and I'm putting it through an MLP. At each position, I get an output. I pass all of these outputs through a softmax. Simple. But then, if you look at it closely, this looks like this, right? I have all of these networks scanning the input, and then their combined output is going to a single softmax. What does this look like? It's just one large network, right? What's the specialty of this network? The lower layers are subnets which are all identical. That's about it, right? So this is just the final layer of the overall MLP. You can just call it a giant MLP. Same thing with 2D. I could have a flower detector, which detects flowers in a little rectangular area. I can scan the input. And eventually, when I've scanned every location of the input, I can pass the entire collection of outputs through a max or a softmax or an entire MLP. And this should still solve the same problem. It will tell me if the image has a flower in it or not, right? So, lady at the back, can you shut your laptop? Yes. Laptops are shut in this class, okay. So, here again is the pseudocode for it. I'm scanning left to right, top to bottom. At each position, I'm pulling out a little segment of the image, roughly the size of a flower. I pass it through an MLP. I get a collection of outputs, one per location. It's double indexed because you're scanning left to right and top to bottom, and pass it through a softmax. But then once again, this is just one giant network. And so the key component is that it has many subnets at the lower layer, which are all identical. That's the only difference. And so this network now is shift invariant. Both this network and the one that we saw earlier is invariant to a shift in the pattern. So I could just replace this entire thing. The softmax is the final layer of the overall MLP. I just call it a giant MLP. But what we have done by scanning and combining the outputs is to construct one single network, which is invariant to the position of the pattern that you're looking for. Right? Questions? Okay, so there's a first poll. I've lost matters. Okay, I'm going to give you 10 more seconds, guys. All right. What's the answer to the first one? Second? True. Both of them are true, right? Okay, let's continue. Please shut your laptops again. Yeah.
Suppose if you're doing multiple frames and in the second frame is like it's just a part of a flower coming in. Does that?
That's like having something that's off frame, right? So something that detects a flower is not going to detect just the left-hand corner of the flower. So now I'm just going to introduce a little change of pictorial representation. So do you mind shutting your laptop, lady? Yes, all of you. Okay. What is your name? Can you get your name tag up?
Oh, right.
Yes, so get pass her a sheet. So I need to have something better than lady to address you with. So this is the kind of MLP that we were drawing. Now, when I scan with an MLP of this kind, the picture I get looks like this. There's something wrong about this picture. What is wrong about this picture is that it seems that this guy occurs later in time than this one. It seems to be a temporal ordering within the layer itself, which we know is not true. And so I'm going to redraw this picture, like, instead of having a picture of this kind, where the layers themselves seem to have a temporal ordering within them, I will redraw them vertically like so. So it gives you the idea that this entire computation happens at one time. This is the first layer. The one above it is the second layer. The one above it is the third layer. And every neuron in the first layer connects to every neuron in the second layer. This illustration making sense to you guys? Right, I'm going to use this. And so to simplify it, I'm just going to redraw the picture like so. When I have an arrow between two blocks, it means that there's an entire collection of neurons which connects completely to a second set of neurons in the next layer. And all the computations are happening in one column at one time. And so a computation of this kind, which is scanning with a network which is looking at 2 inputs at a time and striding by 2 inputs at a time, would be redrawn in this manner. So this is the picture I'm going to be using. Okay. And if I'm scanning with a stride of 1, this is what the picture will look like. So let's go back and see how this network can be trained. This network is solving a problem. It's just telling me, is there a flower in this picture or not? Or does this recording have the word welcome or not? Now, when I go back and give you this solution, right? This solution assumes that when I build the flower detector, I have data, pictures of a flower roughly the size of that box. And I have positive instances and negative instances. And that's how I can train this flower detector and combine the output, right? But is this really necessary? It is not. Why? Because we recognize that the whole thing is just one giant network, right? And because it's one giant network, I can do this. I can train the network all at once, except I will give it collections of data where I have some recordings which have the word welcome in it, somewhere in it, other recordings which do not, or some images which have the flower somewhere in it and other images which do not. I will not be telling the model exactly where the flower is. It must nonetheless be able to learn the detectors, lower level detectors, through gradient descent. And that's because it's just one giant network, and we know a giant network of this kind can learn from data. The key distinction is that these are shared parameter networks. So all of these subnets have identical sets of parameters. Similarly, all of these subnets have identical parameters. So we're going to have to modify our training paradigm to account for the fact that the parameters are identical. Now, so these are all the lower level subnets are identical. They're all searching for the same pattern. What this means is that when I'm training the network, well, if I perform back propagation and I update the parameters for, say, this copy of this instance of the subnet, that update must reflect on all copies above. And every one of them must copy over whatever update was made to the lowest subnet. That's how you make sure that all of the subnets are identical, right? So how does this work? This business with shared parameters. To see how the business with shared parameters works, let's consider this. It's a generic concept. You can always decide completely arbitrarily that that connection there and this connection here are going to have the same value. There's nothing special about the specific structure that we just saw. So let's say you decided that in this network, this connection and this connection are going to have the same value. What does this mean? It means that there's a common value WS which is being applied to both Wij(k) and Wlmn. And so if I were to train, anytime I want to update this parameter, that means this guy must also be updated by the same amount, or more generally, this common value must be updated, and that must be distributed across all the elements which copy that value. So now if I actually draw the influence diagram, now you guys are already familiar with the notion of influence diagrams, right? Here's what it looks like. This common value Ws influences Wij(k). It also influences Wlmn, and both of them are going to influence the divergence. What are we trying to estimate? We are trying to estimate this common value Ws, which means we need the derivative of the divergence with respect to Ws, right? There are two paths to it. So what is the formula for the derivative? It's going to be down one path, the derivative of the divergence with respect to Wij(k) times the derivative of Wij(k) with respect to Ws, times plus the derivative of the divergence with respect to this weight times the derivative of this weight with respect to Ws, right? That's what we have here. What is the derivative of this guy with respect to Ws? Anybody? Can you say that aloud?
1.
Why? They are the same. It's just copying it, right? So which means that this derivative and this derivative are both the same, which means that the derivative of the divergence with respect to this common shared value is simply the sum of the derivatives of the divergence with respect to the individual parameters which share that value. Make sense? And so when I'm training the model, what I would do is to perform back propagation to compute the derivative here. I would perform back propagation to compute the derivative here as well. And then I just sum them up. And that's going to give me the derivative with respect to the common shared value. Okay? And so here, when I'm training this network with all of these identical subnets, all I really need to do is to provide the data, the model with data, positives and negatives, pictures with flowers in them, pictures without flowers in them. And I would compute my divergence here. And now if I want to update this edge of the scanning network, it means I must also update the other edges which are all red because they're all the same network, right? And so I would compute the derivative of the divergence with respect to every one of those red guys and sum them up. And that is the derivative that I'm going to be using to update this, the value of the weight associated with the red edge. So also with any set of shared parameters. That makes sense to everybody? You guys at the back, that makes sense, right? Okay, just because we are off Zoom doesn't mean that the paradigm changes. I'm going to be expecting some pretty enthusiastic nods of your head, even if you're at the back of the room, just so that I know I can go ahead and that I haven't blocked, okay? And guys on Zoom, same goes for you. Please say a yes or no. I don't mind if it's loud. And so here is what the training paradigm is going to look like. You have this set of edges shares a common value. This set of edges here shares a common value and so on. So you have sets of weights which have the same value. And so when we want to perform updates, we want to update the common value for the set. So for every element in this, so which means we want to compute the derivative of the loss with respect to that common value, which we would then use to update this common value using gradient descent. And this common value is going to be distributed across all of the copies of this value. We need this derivative here. And this derivative is simply going to be the sum over all copies of that value of the derivative of the divergence with respect to that copy of the value. And that can be computed using back propagation. So here in this case, if I want to compute the derivative of the loss with respect to the value that applies to all of these guys, I'd be using backprop to compute the derivative here, here, and here, sum them all up, and that's going to give me the derivative with respect to the shared Ws, which I would then use to update the parameter value, right? Do you mind closing your laptop there? Please shut your laptop. Thank you. Right, yes.
So when you say that you back propagate and update the weights like by taking the sum,
So wouldn't it be like basically normalizing a particular value for each of the edges that you are like finding?
There is nothing, there's no normalization. You're just performing raw back propagation. You have just decided a priori that those three guys are the same parameter. That's it, right? There's nothing else going on. This is just straight up back propagation and accumulation of derivatives. Okay, and that term, these derivatives are going to be computed using backprop. Yes?
I just had a question related to the red lines. Are all the red lines the same weights?
Yes, because this is a subnet. This is the scanning network, right? So as it scans, it's looking at each position. So this network is the same as this network is the same as this network, which would mean that this weight and this weight and this weight are the same. That's it, right?
But since it is taking a different part of the image and
Remember, we are scanning for a flower.
right.
So does the network change depending on which image it looks at? Right. So basically, from our point perspective, what we have is an image of this kind. There's one copy which looked at this. This was looked at by the network. This was looked at by the network as well, but these two are the same network, right? So nothing changes. Any other questions? No. Okay, so position invariant pattern classification can be performed by scanning. One-dimensional scanning for sound, two-dimensional scanning for images, but you can also do the same scanning for higher dimensional data, 3 dimensions, 4 dimensions. There's nothing, going to higher dimensions doesn't change the basic idea. Scanning is equivalent to composing a large network with identical subnets. And when you want to learn in these networks, the back propagation rules must be modified to aggregate the derivatives for all the elements that have the same shared value S-squared.
So since you're using a max to combine all of your layers, wouldn't the layer with the highest value be the only
We
one?
don't necessarily use a max. Max is one of them, but I said you can also use softmax, which is more likely. And sometimes you just pass it through an entire MLP, yes.
People can't hear the questions you say.
Okay, so the question was, since we're using a max, wouldn't it be just the largest entry that gets the gradient? And that would be true if we use the max. But for a softmax, or if you used an MLP, then there would be other copies of it getting derivatives too. So now, let's take a closer look at how the whole scanning works. This is my network. Again, this is my MLP, but I've just drawn it using the vertical notation, just for to emphasize the point that that entire computation is being done at one time, right? So now, if this network were to analyze this image, this portion of the input, remember it's scanning, right? Then what would happen is that the first layer is first going to generate outputs. Each neuron in the first layer is going to generate outputs shown by those 4 gray circles. Then those 4 outputs are going to be fed to the second layer, and each neuron in the second layer is going to generate its outputs shown by the 2 green circles. And then the second layer neurons would feed the third layer, and that is going to generate its own output. So then this computation is going to be done at the first position, and then the second position, and the third position, and so on, all the way till the end of the input. And the final layer outputs are then combined using your max or softmax or MLP or whatever to take a decision for the entire input. So all the little circles are identifying all the local variables that are computed when you're analyzing this input. So this here, for example, are the outputs of the 4 first layer neurons in the first window, right? And the corresponding one up there are the outputs of the 2 second layer neurons in the first window, and so on. Now, let's say that when I'm doing the computation, the first layer is in a hurry. It's not willing to wait for the second layer. So it does its computation. And before the subsequent layers perform their operation, the first layer goes off and computes its outputs for the entire input. And then the second layer kicks in. And the second layer, and the rest of the network kicks in. And the rest of the network reads the outputs of the first layer in the first window and generates its output. Will the output at the topmost position now be different than in the previous case where the entire network analyzed that window before progressing? So yes or no?
Yes.
Would the output be different? It should not be different, right? You're using the same 4 values regardless of whether the entire network analyzed it there or the first layer went off and did the whole thing, right?
Activation between layers.
Pardon me?
Are we using activation between layers?
It's just a layer. The layer is basically, as we define the perceptron, it computes an affine term and then applies an activation, right? It doesn't matter. The point is the first layer does its computation. If the first layer runs away, the second layer can still operate on the first layer's outputs, and it's going to get the same value as it did if the first layer waited for it to perform its computation, right? And so now the second layer too, so the output here does not change due to the reordered computation. That making sense to all of you guys? Right, okay. And so now the second layer too can do the same thing. The second layer can now go off and scan. What is it scanning? Is it scanning the input or is it scanning the first layer's outputs? And now if I take the output of the second layer and pass it through the third layer, will that output be different? It's still going to be the same, right? And now the third layer can go off and do its scan, right? And so all we did was reorder the scan, and the final output should still be the same. Now, this is much more obvious when you look at it in terms of code. When you look at it in terms of code, what did we do? We were scanning left to right. We were pulling out a segment, and then we are analyzing the segment, generating an output, and passing it through the final softmax when all the segments were analyzed. But within any segment, what did we actually do? This little bit, this MLP segment, was the patch in blue. At that location, you went through all the layers of the MLP. And then you computed an affine term and put it through an activation. And so if you look at where all of the fun stuff is happening, now observe that there's an if clause. That's because only the first layer is looking at a window. The second layer is looking at just one column, right? So the if clause is basically stating that if you're in the first layer, you want to look at a section of the input. But if you're in the second layer, you're looking at just one column of numbers from the previous layer, second and further layers, right? But all of the fun stuff is happening inside the gray box. So the 2 outer loops are interchangeable. If I flip the 2 outer loops, the outermost loop is over time, the second loop is over layers, right? If I flip the order of these 2 loops, would this change the final output? Because all of the computation is inside the innermost loop, right? So changing the loop indices is not going to change the output. And so this is basically what we did. We just changed the loop indices. Same thing, if I was doing this with pictures, then I'm scanning for the picture. At each location, the entire region is being passed through an MLP, right? So the input layer is just the input. And then you have hidden layers and you have subsequent layers for here. Now, what happened in our first case was that we had the entire network look at the entire window, and then it scanned, and the network was producing an output at each position, right? And so and eventually, you got one output from each position. I've arranged all of the outputs in the same manner as the input itself, just to show you that this is basically a map of the input. Each dot to the right is representing the output of the network for one specific location in the input. And then that entire collection is being put through the softmax, right? Now, I can change this. Let's consider just the first neuron in the network, the top left neuron. Let's say that neuron by itself just goes on and performs all of its analyses without waiting for the rest of the network. Or indeed, we can say that every one of the neurons in the first layer goes off and just scans the input without waiting for the rest of the network, right? Now, if I want to find out if there's a flower in this location or not, what must the rest of the network do? Anybody? What must it look at? Which one? First layer output where, right? So take a look. here, this first neuron is generating its outputs at each of these positions, right? Which was the output it generated when it was analyzing this bottom right box?
Bottom right ball.
The bottom right, right? So this guy here is what this neuron generated when it was looking here. This guy here is what the second neuron generated when it was looking here. So if the overall networks must decide if there is a flower in the bottom right, which of these values must it look at? Just the bottom right, right? So more generally, if it wants to decide whether there's a flower in this box or not, it must pick up the values that the first layer neurons generated when they were analyzing that region of the image. So basically, because I've arranged the pixels in the same shape as the input itself, I just had to pick up the activation value corresponding to that location in the image and pass them through the rest of the network. And that's going to tell me if there's a flower in that location or not, right? And so we've sort of let the first layer do its thing before the subsequent layers did their operations. But then now the second layer can also go ahead and scan in the same manner. The second layer neurons can just go off and observe now that the second layer neurons are looking at all of the outputs of all of the first layer neurons. So the second layer neurons are now reading one value from the maps produced by each of the first layer neurons in order to analyze any specific location in the input, right? And now the second layer neurons can go off and scan the entire input, and they would produce their own map. And then if I wanted to find out if there was a flower in that location, the next layer would just read the value that the second layer neurons produced when they were analyzing that location. And you'd get the output, right? And now the third layer neurons can also do the same thing. They can scan the outputs of the second layer neurons and produce their own maps. And then you can pass the whole thing through a softmax, right? We've reordered the computation. So if you look at the third layer map outputs, and if you want to know if there's a flower here, you just need to look at what the map value was at that particular location. So we've reordered the computation, but the final output is still going to be the same. And to see why this works, again, we can look at the pseudocode. So earlier, I was scanning left to right, top to bottom. At each location, I was pulling out a segment of the image, and I was putting that segment of the image through an MLP. I was collecting all of these outputs and putting it through a softmax. But then let's look at what this MLP is. Within that MLP, I'm going through layers. Within each layer, I'm reading the outputs from the previous layer, computing an affine term, and putting it through an activation. Only the first layer is looking at a window of the input, right? Only the first layer was looking at an entire window. Subsequent layers were reading one value from each map, if you'll remember the picture, right? So here, this guy was reading the second layer neurons were looking at one value from each map, but the first layer neurons were looking at the entire window. So the pseudocode has this if clause. If you're in the first layer, look at a window. Subsequent layers are just going to read a value from their maps produced by previous layers. But hold that thought for now, we'll get back to it. But the point is, all of the action is inside the innermost loop, yes?
Does the user specify the window?
Hang on with me, right? Let's get to the end of class. Nora, do you want to go out and wash your face or something? You're falling asleep. Okay. All right. So if I change the order of the loops, will this change the final output? No. So which means that I can just pass the layers out there, flip things, and everything still works, and the final output is still the same. That's basically what we just did when I reordered the computation. So reordering the computation should not change the final output, and that's simply because all of the action is within the innermost loop, right? So the story so far, position invariant pattern classification can be performed by scanning the input for a target pattern. Scanning is equivalent to composing a large network with shared subnets. The operations on scanning the input of the full network can be reordered as scanning the input with individual neurons in the first layer to produce maps. Then scanning jointly scanning the maps of the outputs of all the previous layer neurons to produce subsequent maps and so on, right? Now, the thing is, when you go from the second layer onwards, you're jointly scanning all of the maps, right? Because you're reading the outputs from all of the previous layer neurons. So here's your second poll. Yeah. Okay. Give you 15 seconds, guys. This should be easy. Okay, can someone from Zoom answer these questions? First question, true or false? Someone on Zoom? I know there are people on Zoom. Somebody reply, please. True or false?
True.
True, okay. Second one, true or false? Also true? Okay. Do you guys agree? Yeah. Let's see. So scanning an input with an MLP is mathematically equivalent to first scanning it with the individual neurons and then scanning the output maps of the first layer neurons with the rest of the network. True. The operation can be recursed. Scanning the output maps of the first layer with the rest of the network is equivalent to just scanning it layer-wise, right? So now let's get a little closer, right? What do the neurons do? The entire MLP looks for a flower-like pattern in each position. So that's all you're really interested in. The MLP must look for a flower-like pattern in each position, right? So the first layer neurons look at the entire window at this point. And then the second layer neurons, each of them is just going to be looking at, so these guys are looking at the entire window. The second layer neurons are just looking at one element from each of the first layer maps, the way we just presented it, and then the rest of it is going through, right? So subsequent layers only look at a single pixel from their input maps. I can distribute this pattern across multiple layers. How? The first layer can look at a smaller region of the input. And so the first layer neurons could be looking at maybe something the size of that white box and scanning the input like so and producing its map. Then the second layer neuron can look at a small box, a small rectangular region of elements from the outputs of the first layer maps. So which portion of the input is the second layer neuron looking at? It's looking at any portion of the input that was considered in computing any of these 9 elements. And so the second layer neurons are going to be effectively looking at the entire window. And then the subsequent layers can just operate off these maps, right? And so what you can learn, the second layer neurons, for example, learn patterns at the size of the window. So this guy, the first neuron might know, for example, to fire if the first second layer neuron could fire if the first layer neuron found something in the top left positions, the second one found something in the top right, the third one found something in the middle, and the fourth one found something at the bottom right. So the second layer neuron is basically firing in this case if there are 2 petals. There's something in the middle, a stamen in the middle, a petal at the bottom right corner. And each of those is detected by a different first layer neuron. So what is happening here? In the first case, the entire responsibility, when we were doing this, the entire responsibility for finding flower-sized patterns was imposed on the first layer neurons. The features that the first layer neurons were detecting were entirely flower-sized, which are very complicated. When we distribute it in this manner, we are saying, let the first layer neurons look for something smaller, maybe the size of a petal, the size of a sepal, the size of a stamen. And the second layer neurons are aggregating this information in position with arrangement to take their decisions to get the larger pattern. So you've distributed the pattern detection over multiple layers. And so now the second layer neurons can, of course, go ahead and scan, right? They can produce their own scan of the maps produced by the first layer neurons. And now, of course, it has to scan, right? It has to scan all 4 maps. So for example, if the second layer neuron, if a neuron is going to say, I will fire if there are 2 petals to the left, something in the middle, and a petal to the bottom right, it has to be scanning all of the maps of the first layer neurons, because each of the first layer neurons is looking for a different sub feature, right? And then it can generate its output. And now, if the next layer neuron wants to decide if there's a flower in the top left corner, it just has to look at the elements produced by the second layer neurons when they were analyzing this region of the first layer maps. Did this make sense? It might sound confusing, so I want to make sure it made sense. Yes, no? You guys on Zoom, can I hear a few yeses? Did they type some yeses at least? Okay, thank you. All right. And now, the whole thing can go through a softmax, right? Now, this is still scanning. That's the point. We haven't done anything magical. It's still scanning, and it's still scanning with a shared parameter network, except there's a lot more sharing of parameters. So to look at this, let's say the second layer neuron is looking at these 9 elements from the maps of the first layer neurons. What does this mean? Now, each of these 9 elements were computed by scanning with a first layer neuron, right? So it's like having 9 copies of the same neuron looking at different locations. So also this guy here, these 9 elements is like having 9 copies of the red neuron, each looking at a different region of the image. And so the second layer neuron is actually reading all of these 27 values. But although there are 27 inputs going into the second layer neurons, there are only 3 unique sets of parameters, because all of the black neurons have the black entries. They're using the same neuron. They have the same parameters. The red values, they're all being analyzed by the same neuron. They have the same parameters. These blue guys, these are 9 copies of the same neuron, so they all have the same parameters. So although you have 27 entries going in, you have only 3 sets of parameters being used to compute those 27 values. And so the overall network is still a shared parameter network, except that the sharing is not only across subnets that analyze different regions of the input, but within each window itself, you have additional sharing, right? So I can do the same thing by building this over 3 layers. The first layer neurons could be looking at an even smaller region of the input and scanning it. The second layer neurons could now be looking at little windows of the outputs of the first layer neurons. And so what the second layer neuron is analyzing is any region that was considered in computing any of these 4 values. So that second layer neuron is looking at maybe that red box. Then the third layer neurons could be looking at little windows in the maps of the second layer neurons, which means they're effectively looking at any region over here that was considered in computing these 4 guys, which would be this patch, which in turn represents any region in the input that was used in computing any of these guys, which is the big window, right? And so I'm distributing the pattern over multiple layers, and now the entire process can be recursed. So instead of just having only the first layer be responsible for getting flower-sized features, you can compose the features over many layers by looking at little windows in the maps produced by the previous layers. Now, there's something special going on over here. If the first layer neurons were entirely responsible for looking at flower-sized windows, then you don't really have to arrange their outputs as a map, because the position doesn't really matter. After that, it's just a bunch of individual values, right? But when I distribute the pattern over many layers, then what is critical is that the output of this neuron is actually arranged in the same shape as the input itself. That's the only time I can actually look at a window, right? Similarly, the output of this neuron must be arranged in the same shape as the input itself. That's when I can look at a window. So the arrangement now becomes important. And once again, if you actually look at it closely enough, it just ends up being a gigantic shared parameter network. It's just that you're still scanning the entire input with an MLP, but within the MLP itself, you have many levels of shared parameters. That making sense to everybody? Oh. Can I see a wave of hands if it made? Okay, thank you. Appreciate it, right? So here's what happened from the pseudocode point of view. Earlier, he was scanning left to right, pulling out a segment and analyzing it with an MLP. But then, when we rearranged it, we were going through the layers. Within each layer, we were scanning left to right, top to bottom. And at each position, if you were in the first layer, you were pulling out a window. If you were in subsequent layers, you were reading only one element from the maps of the previous layer outputs. And so for this first layer alone, there was a window of the input being pulled out. For subsequent layers, you were just looking at one value. It turns out that when you distribute the scanning in this manner, the pseudocode actually becomes simpler. It just says that at each position, within each layer, you just pull out a little window of the maps produced by all of the previous layer neurons, and then compute an affine term with those and put them through an activation. Okay, so here I'm scanning. At each point, I'm pulling out a little window from each of the maps of the previous layer neurons, and then I'm computing an affine term from all of those, and then putting them through an activation. So I'm just sort of rushing through the pseudocode, but you get the idea, right? So this operation of scanning the maps from the previous layer neurons with a window of weights, this is what is called a convolution. And so this entire network is called a convolutional neural network, right? So, wait, is it really 8:49? Yeah. Anyway. And so this is just the same thing in vector notation, right? So here's what happens. You're going through the layers. Then within each layer, scanning left to right, top to bottom. Then at each position, you're pulling out a segment, this little rectangular segment from each of these maps. So here I have a little two-dimensional rectangle pulled out from each of those maps. If I stack them together, it's going to give me a two-dimensional cube. It's a tensor. And so if I were to use vector notation, then what this neuron is computing is a weighted sum of all of these 16 elements. That's like saying that I'm taking this 2 cross 2 cross, what is this? 4 cuboid. I have a corresponding 2 cross 2 cross 4 set of weights. I'm doing an element-wise multiplication with all of those, adding a bias, and then putting it through an activation. We'll see this in more detail in the next class, okay? So just giving you an idea. Same thing with, if you're doing this with 1D. In 1D, let's say I was analyzing this input for the word welcome using this network here. 4 neurons in the first layer, 2 in the second, 1 in the third. And then at each location, so the first layer neurons are going to compute all of these values, but the first layer neurons might just be looking at a small window of the input. Now the second layer neurons are going to be looking at a window of the outputs of the first layer neurons. And so by looking at a window of the output of the first layer neurons, they're looking at anything that was used from the input in computing each of these 3 columns, which is a larger window of the overall input. And then the third layer neurons over here, if they want to analyze a larger region of the input, they're going to be looking at a window of the outputs of the second layer neurons, which corresponds to a much larger window of the input itself. So as you go through the layers, because each layer is looking at a window of the outputs from previous layers, you're looking at more and more of the original input itself. And so the final layer is going to be looking at a wide region of the entire input. Okay, questions? No. And so you can just continue this, right? And then the final perceptron to aggregate them is aggregating the evidence. Does this recording have the word welcome in it? This structure, when you're scanning in one dimension, It has a name. It's often called a 1D convolutional network, but the more traditional name is a time delay neural network. If you've ever encountered a TDNN, this is what it is. Okay? Here's a book.
Messages like the exact same messages, so I have a formatted message. And I just respond to every student. It's really funny.
Okay, 15 seconds, guys. All right. The first statement, true or false? Second one, third, fourth. Okay, let's see. Thank you, right? Non-distributed scanning does not require the output to be arranged in the same shape as the input. But once you begin distributing it, you want the shape to be maintained. You want these outputs to be maps of the input. Otherwise, the whole notion of a window makes no sense, right? So why distribute? Why do we bother with distribution? There are multiple reasons. Distribution forces hierarchical representations with localized patterns, so it's more generalizable. It requires fewer computations and requires far fewer parameters. Let's go through these one at a time. Now, let's look at this business of hierarchical representations with localized patterns. Remember, way back when we wanted to build a classifier for this double pentagon, did we just throw the double pentagon and did every neuron try to compute a double pentagon? No. What happened? The first layer neurons computed individual edges. The second layer neurons computed individual pentagons. The final layer combined the pentagons. You wanted to distribute the structure across many layers. And why did we do that? Lecture 2? Yes.
To reduce the number of neurons.
This gives you a much more expressive power. If you want to do this with a lower number of layers, you're going to need an enormous number of neurons, right? So by distributing things in this manner, where each layer looks at simple patterns from the outputs of the previous layer, you actually simplify the entire problem and make the network simple. So distribution is a great thing to be doing in terms of network parameters and efficiency in learning and modeling. So ideally, we must encourage such hierarchical learning. It's more data efficient. It's also more parameter efficient. What about fewer computations and fewer parameters? Let's see how. So I'm going to use this example here. I'm trying to scan, let's say, each of these vectors. If you had a speech signal, it's going to become a sequence of spectral vectors, right? So let's say each of those little black vertical bars represents one vector of some d dimensions. And now, if I want to analyze a window of the input that's 8 vectors wide, if I were doing a non-distributed scan, the first layer is going to be looking at 8 inputs. The second layer is going to be looking at just the outputs of the first layer. The third layer is just going to be looking at the outputs of the second layer, right? So how many parameters? So if you were just striding by 2, this is the entire set of computations that you'll be performing, right? At each position, that entire column of values is being computed. And I'm not going to draw the individual circles. I'll just draw vertical bars. So this is just to make the pictures less ugly, okay? Now, if this layer had N1 neurons, and if this layer had N2 neurons, and if that third layer had N3 neurons, how many parameters does the entire network have? Keep in mind that each of these bars is d wide, and the first layer is considering 8 bars. So how many parameters would it have? Anyone? How many parameters would the first layer have? There are N1 neurons. Each of them is looking at 8 inputs of depth d, right? So it's 8d N1 neurons in the first layer. How many parameters would the second layer have? Can you say that aloud? N1 times N2. There are N2 neurons in the second layer. Each of them is reading inputs from each of the N1 neurons in the first layer. So there are N1, N2 neurons, right, parameters. And the third layer is going to be N2, N3 in the same manner, right? So this is the number of parameters that you'd have. This is more generally, if you're looking at a width of L, it's going to be LD, N1, blah, blah, okay? So I'm ignoring the bias term because the bias term is just a very small fraction of the entire computation. And so this is the compute that you'd be doing. If you are stepping forward by 2 vectors at a time, this entire set of parameters is being pulled into action for every 2 vectors in the input. So the entire set of computations you'll be performing is shown in this picture. Now let's say instead of having this one guy be responsible for the entire set of 8 inputs, I want to distribute it. How would I distribute it? So instead of having one layer look at 8 inputs, what I would do is to have something which is maybe this, so maybe this small, right? Look at two inputs at a time, and then all of them could be combined, right? If I did this, I'm still looking at inputs, 8 inputs at a time, except that the first layer, thank you. So it turns out that it doesn't always run away, right? This guy is being reused 4 times, right? And so here, I could just have my first layer scan the input with a window of size 2. And then the second layer is looking at 4 of these inputs. The network is still looking at 8 inputs at a time, right? But what about except that the 8 time step wide input is now being distributed over 2 layers. It's not just 1 layer. The first layer is only looking at 2 inputs. Subsequent ones are aggregating stuff, right? How many parameters would I need? Let's say this guy has N1 neurons and this guy has N2 neurons. How many parameters does this one need?
2D N1 in the first.
It's just 2D N1 in the first, right? 4 N1, N2 in the second, and then N2, N3 in the third, right? So these are all the parameters. It's going to be 2D N1. Then these 4 all have different weights. So 4 N1, N2 plus N2, N3. This making sense to everybody? Okay, now if I had a second network which was using the same number of neurons to perform this computation, how many neurons would I have in the first layer of the second network? To be equivalent, like I said, here it's like saying I'm going to take a small portion of it and scan, right? I have 4 of these. So this one is like having 4 blocks. This is 1, this is 1, this is 1, and this is 1, except the 4 blocks are all identical. We made them shared parameter networks, correct? And so the corresponding equivalent for the non-distributed scan is going to be 4N1 in the first layer, N2 in the second layer, and N3 in the third layer. How many parameters does this guy need? This is 8 times 4, 32 N1D, right? The second one is 4 N1, N2, and the third one is N2, N3. So if you actually compare the number of parameters over here, this is 2D N1 plus 4 N1, N2. That one is 32 N1 plus 4 N1, N2. There's a factor of 8 compression in the very first layer just by sharing the parameters. And this is obvious, right? It is obvious because earlier, every one of these copies had individual parameters. Now we are saying all 4 of them have the same parameters, right? Similarly, and then of course, there's a softmax, right? So this is how the scanning is happening. Observe that it's still scanning with a shared parameter network, except that within the network itself, there's additional sharing of parameters, right? So now, it also saves in compute. Let's see how this saves in compute. So let's say I perform this analysis in the first computation in the first window, right? First window of 8. Then if I step forward by 2, do I need to recompute the entire network? Which portions do I need to recompute? So these guys have already been computed when I analyze the first input, first window, right? Similarly, when I go to the next one, these guys have already been computed. So as you keep going forward, you're reusing computation from previous scans. So here, those three guys are being reused in the second location. So you get this large additional benefit from the fact that scans at neighboring positions share the computation of lower level blocks. So you can see that first, there's a huge reduction in the number of parameters because you're sharing parameters within each layer. So again, go back. If you had a non-distributed scan, you'd have these four, maybe you have 4 neurons over here. Each of them would have its own individual set of parameters. Here you're saying that these 4 neurons all have the same parameters. So you reduce the number of parameters by the sharing. And second, because of the manner in which the scanning happens, you actually end up saving computation, right? So I can do this by distributing this over more layers. I can say that instead of having this first guy, what's happening here? Let's see. Look at 4 of them. I can say, this is run out of battery. Yeah. I can distribute the scanning over 2 layers and say that the second layer is only going to look at 2 windows from the 2 outputs from the first layer. And the third layer is going to look at 2 outputs from the second layer. The overall network is still analyzing an input of what width? 8, right? So the overall network is still analyzing an input of size 8. But then how many parameters do I need over here? Can someone tell me? It's just 2n1 and 2d-n1, right? Plus 2n1 and 2 plus 2n2 and 3, right? And if I want to compare this with what would happen over here, that's going to be 32n1, 32d-n1 plus 8n1 and 2 plus 2n2 and 3. So again, you can see that even in the second layer. Now, if I distribute this over 3 layers, I begin saving parameters in the second layer. And once again, you can see what this happens. If this guy goes up and says, you have a bunch of neurons, if I decide that these guys are the same neuron, then they have the same parameters. And so I'm saving parameters over there, right? And so you get massive reduction in parameters. And then you can once again see that you can now save computation even in the second layer by reusing reusing computations from earlier positions. So if you were scanning this input to analyze a window of width 8, so these are all the computations that you'd be performing in the first position, the colored ones. When you go to the second, third position, you're going to be reusing these 3, right? And so you're going to be reusing computations from the second layer as well. So the more you distribute, and here's a little more complex model, but then shows you the same thing, that you can you reuse a whole lot of computation. So if this is the model that I'm actually analyzing the inputs with, when I go over here to the next position, to the second location, which are all the elements that I'm reusing in terms of compute? Can you point out? So if this was my basic network, right? If I stride forward by 2, then that is this network. It's hard, once I draw the whole thing, it's hard for you to identify which the scanning MLP is because the picture looks complex, right? But can you see the scanning MLP in this picture, right? It's the guy that starts from here and does this, right? And it's reusing this entire portion of the computation from the previous location. And so this is a convolutional network, standard convolutional network. But then the idea behind showing all of these pictures is to explain to you that although we think of it in terms of convolutions, it's really just scanning with a shared parameter MLP. You're always scanning for patterns, okay? And the point of having this distribution and of the parameters over many layers is that it gives you a reduction in the parameters because within each layer you're reusing parameters, and it's going to give you a great reduction in compute because you can reuse the computation that you've already performed, right? So that was for 1D. But you have the same thing with images, right? I'll skip these slides, but I actually worked through some arithmetic that I'd like you to go through on the slides to see how much you can save. And so for a very trivial model with just 7 neurons, if I did not distribute the parameters, I'd have 1,034 weights. If I distribute them, I end up with 194 weights. So you can see there's almost an order of magnitude for something this small. As the model gets larger and larger, then the reduction can be several orders of magnitude. You can go down from 100 million to 1 million, and the number of parameters that you really need. Questions? Yeah.
So when you say when you're distributing in the non-distributed case, so the number of neurons in the first layer are the same for both, right?
The total number of neurons.
Like in each of the sets, like the bars which you are representing.
Yes. So now the way to think about it is this. In the non-distributed case, you'd have one large bar. In the distributed case, you're going to say these 3 bars are identical. Sub-bars are identical. That's it. Right? That's the way to think about it. Okay? All right, yeah.
How are we modeling the output neurons as per the input in the distributed?
It doesn't matter. So it's basically just this, right? You're getting scans. Where's my pointer? Okay. Once you have the outputs of the final layer neurons of the scanning MLP, beyond that, there's additional computation where you could just aggregate all of those into a softmax. That's what we do these days. In earlier days, you'd actually pass the whole thing through an MLP.
But the poll said that we need to, the previous poll said that we need to model the output layers of the output neurons as per the input layer.
Which one? I may have lost a point here. Too many slides, right? Where? Which one?
Yeah. Distributed scanning requires the output maps of the neurons.
The output maps, right? You're not speaking the neurons. You want those things to be arranged in the same shape as the input, otherwise the window doesn't make sense, right? Okay. Questions, anybody? Yes.
I have a question on page 255.
Oh my good God. Okay. Yes.
I don't understand why these two compute the same network.
They're analyzing the same width of input. They're not the same network.
Why don't we need to compute the right-hand side of this?
So when I'm analyzing 2 adjacent positions, these 3 values are the same. They're not going to be changing simply because I scan the network, right? Move the whole thing forward. So think about this. These 4 are the same neurons, right? So whatever values I have computed over here, these locations, when I go to the next location, those same values can be reused here.
Oh, yes.
So
because you can compute in the next.
so our point here was that as you slide, so this is probably the easier one. Look at, these are all the computations that are being performed, right? When I go to the next position, these three do not change, do they?
They do not change.
So I can reuse them.
Oh, gotcha.
Yes, Ishan?
So generally speaking, wouldn't you like that more parameters with there for a network, more information?
So
Like if we use a lot of parameters, wouldn't we like losing a lot?
So the point is, yes, having shared parameters, it's always a trade-off, right? Because you're sort of compressing the number of the number of different patterns that you can actually recognize. But then that comes also with the trade-off that you need a lot less data to train it. Orders of magnitude less, yes.
I see the drawing at there, so you think there are 3 identical things if it's a big block of neurons. So I'm thinking, if we're using 3 layers for the distributed scanning, we are only scan the 8 inputs. But for that one, we are already after we finish the scanning of the 8 inputs, we are also adding 2 further layers of analysis.
No, so this is the entire, say in this case, this is the entire model, right? There's no further layer of analysis.
Yeah, the non-distributed.
So in the non-distributed one, if you had it, yes, I mean, beyond N3, it's like having a softmax. You could have more things, right? So it's like saying I'm distributing over so many layers, and beyond that, I'm not distributing. You could be doing, so we're going to run out of time. But if I have a network of this kind, I could decide to distribute just here, meaning shared parameters over here. I could decide to have shared parameters here and here, and so on. So the number of layers over which you can actually decide to share parameters is up to us, right? So you'll encounter those in your homework. Anyway, so the key intuition is that regardless of the distribution, we can view the network as scanning the input with an MLP. The only difference is the manner in which parameters are shared in the MLP. So again, this block.
Like all the pairs.
Was there a question on Zoom, or is that somebody just talking? Okay, so here, going back here, right? If I wanted to have this network analyze 8 inputs, then it was easy enough for me to say that this first block is going to have 3 sub-blocks which are identical. The second block is going to have 3 sub-blocks which are identical, and so on. And by so doing, I'm reducing the number of parameters. That's the key intuition. And when they're identical, they're looking at more localized regions of the input. Okay? So the story so far, the new information we've added is that the scanning block can be distributed over multiple layers of the network, and this results in significant reduction in the total number of parameters and the compute. Okay, here's a poll. We'll keep this short, only 45 seconds. What? No, you can let it slide. It won't.
I think once you start writing again, it's not going.
That's okay. I have another board behind it. Okay, 15 seconds, guys. Okay, someone on Zoom, can you answer? Is the first statement true? Zoom? Is there anybody on Zoom left? First statement is true. The second one? True or false? And the third? Fourth? The fourth is true? You're not reducing the number of parameter variables you're computing, right? The total number of variables you're computing remains the same in every case. All that changed was the amount of computation that you needed to compute all of these variables. So you're just computing as many neurons in this case as you are in this case. And each of these is an individual computation. So the amount of stuff that you have to store for the next layer is exactly the same. So the memory, there's no reduction in memory, okay? Some final touches, 4 minutes. So we have some terminology, filters and receptive fields, how you can shrink the maps and so on. If I don't go over this, you don't lose anything. We'll go over this again in the next class. But the entire operation can be redrawn as maps of the entire image. Each neuron is basically scanning the input and drawing a map of it. So you can think of each neuron as looking for a pattern. And it's saying, found it, didn't find, found it. It's drawing a map of the detection of the pattern that it's looking for. And so the first layer looks at small subregions of the input, sufficient to say detect petals and sepals and such like, right? The second layer looks at regions of the output of the first layer to put these petals together into something that's more of a larger substructure of a flower. And then the third layer is going to be looking at regions of the first layer input to get flower-sized patterns. And then the final perceptron is looking at all of these to decide if there's a flower in it or not. Now, the scanning is done using a bunch of weights. At each location, you have a weight. So this pattern of weights is called a filter. They also call it a kernel. There's a lot of terminology flying around, but a filter is a common terminology. It scans for the pattern of in the map that it operates on, right? And the region of the input that any neuron looks at, and specifically the kind of patterns that it actually fires for, is called its receptive field. So the receptive field of the first layer neurons is going to be small. For the second layer neurons, it's going to be larger. As you go through the network, it's going to be larger and larger. And if you want to find out which patterns the neuron actually responded to, for the first layer neurons, it's remember that neurons are effectively just correlation filters. They're just looking for, how the weights align with the inputs. So you can just look at the weights of the first layer neurons to find out which patterns it's looking for. As you go deeper into the network, it becomes more complicated to analyze this, right? You lady there, can you turn off your phone? Upside down, please. Thank you. So, and we have this terminology called flattening, where we just, the final layer neurons are, neuron outputs are finally just passed through an additional processing, which could be max, softmax, or whatever. For the final layer alone, you no longer need to actually keep it arranged in the same manner as the input, because it doesn't really matter, right? And also when you're scanning, you don't need to take a step which is exactly 1 pixel wide. You could be taking steps which are more than 1 pixel wide in each direction. So this is called a stride. So one of the things that happens when you take a stride that's larger than 1 pixel is that your maps begin to shrink by the amount by which you take a stride, right? This is going to result in a reduction of the size of the maps, and it can happen at any layer. If you take a stride of size S, the map is going to reduce by size S in each direction, so the net reduction is S squared. So basically, when you're scanning, you'd be striding, right? That's taking a step with a stride. And then you have additional things like accounting for jitter. It doesn't really matter whether, if a petal has moved by 1 pixel, does it stop being a flower? It doesn't. And so for having, to account for jitter, we perform an operation called pooling, where we look over regions of the input to decide if that pattern fired anywhere in it. Again, this is basically doing at the small scale what we are doing in the large scale for the entire image. Remember, if you wanted to see if there was a flower, we took a max for the entire flower. You could do the same thing within subregions. That's pooling. And so here's the overall structure, which would have convolutions, maybe pooling, and the whole thing is a CNN. We'll go into more detail in the next class. I'll stop right here. And obviously, scanning and convolutions is not where these things started from. But that's really what's happening. There's nothing new with convolutional networks that we haven't actually learned when we were learning about MLPs. Beyond that, it's just efficiency in terms of parameters through sharing parameters and efficiency in computational terms. So we'll see more in the next class. Thank you. It's decided that these two are going to have the same parameter.
If you haven't done an name tag, please get one. So